Hey, so I actually have two videos up for the Fox V3 helmet. If you're into the nitty and gritty and a lot of the tech details, you've come to the right one. I'm going to talk to the doctor behind Fluid Inside in this piece, along with the senior engineer that was in charge of this project at Fox. If you want a little bit quicker overview, hit the link in my description below for Mark Finley. He's the global marketing director for Fox, and he goes over it. But if you want to sit through and hear all my tech questions about the design of the helmet, then you've come to the right video. Hey, this is Mike Lindsay, and I'm here with Dr. Blaine Hoshizaki. You are basically our main guy here, talking to us about Fluid Inside. So I guess the most simple standpoint to start with is, how did Fluid Inside get started? Where did you guys start your research, and under what circumstances?
Well, originally there was a number of commercial enterprises that were interested in concussion in American football, of course, because that was a real big concern a number of years ago. And they approached us to try to better understand how the athletes were getting concussed and to look at ways to mitigate that risk. So we started there, and then we continued to undertake research in head injury in general, like trauma, head trauma. And it was from there that we came to an understanding that rotation acceleration really played a big part in terms of creating the risk for concussion.
So the whole idea of rotational energy and how it affects the brain and how it causes damage, of course, that's I think just in any form of sport, period, it's been talked about. But I do like to think that on the motocross side, we've definitely been fairly invested in hearing about it and learning about it over the past 6-7 years since we had some of our first helmet brands step into technology and start to explain it. So I think at first few years, basically people were trying to digest what rotational energy even was, because we had always just thought a helmet was safe if it absorbed energy from an impact. I don't think a lot of people realize the difference between just basically augering head into the ground versus what rotating does. Once I think people got their head wrapped around what the brain is actually doing inside the skull and understanding rotational energy, I still think there's that bit of a gap with some people in understanding why it's more harmful to you than a linear action. And one of the most simple ones you guys put on a graph is explaining how linear energy would maybe result more in like a hematoma on the brain and more of a skull fracture, where a rotational energy it places a much higher cause of actual brain-related injuries, correct?
Yeah, I think you described it quite well, and that is, if you're going to impact at a very high rate and create a linear response, then your helmet works quite well for that. It absorbs a lot of linear energy, and that's why you don't see, it's not common to see people with traumatic brain injuries in sport. They can happen, of course, but it's less common, and helmets work well for that. The challenge becomes when the impact isn't quite that high of an energy, yet we're still seeing an injury like concussion, which are very important injuries. And so that type of injury, or that level of energy, really creates injury by rotation. And that's really where you can create this trauma, this strain on the brain tissue that manifests itself as a concussion. And so it's a little bit confusing because, of course, we like to think of a brain injury as one kind of injury, just not so bad and really bad. And in reality, brain injuries are not that simple. They are created differently, and they result in different types of injury.
So you yourself, you don't have a background in motorcycles, correct?
I did ride a motorcycle when I was younger, and it was motocross. I'm not particularly good at it, but I did for recreation.
Yeah. So what I'm curious is, of all the studies you've done, whether it be football, baseball, hockey, equestrian to moto, where does moto rank in for you guys in difficulty of design by the fact of, let's just talk about the different speeds, the type of impacts. Does moto have a notably higher or wider range of style of impacts and forces applied than what you see in other sports that you've studied, or?
That's a very interesting question, because each sport is quite different. And one of the areas we also do research in is hockey. And hockey is an interesting sport primarily because you have a low mass, high velocity puck, which can get up to over 100 miles an hour. And then you have shoulders and elbows into the head, which are surprisingly very soft, because the body is soft. So that's a unique impact. Then you have impacts falling to the ice, impacts into the boards, into the glass. And so with all these different parameters that create trauma to the brain in hockey, that's a wide range. In motorsport, it's interesting because you can hit the ground and the different angles matter. And the big challenge around motorsport is the velocity that these guys are going. And sometimes when they leave the bike, they're 10 feet in the air. And so trying to accommodate and understand how that creates a risk for concussion is unique. And for us, we had to look at a lot of video and look at the angles that they were going into, the characteristics of the dirt that they were hitting, to really begin to understand that this really describes the risk associated with concussion. So for us, that was kind of a bit of a challenge. One of the reasons or hints that we got was we did a big study in equestrian. And it's very similar in that they're on turf, they're on softer ground, and they're coming off a horse that's at relatively high speed.
How much does testing for moto change for you guys because of the style of testing that we currently undergo for, just the basic certification for helmets? How different is it from other sports out there, or is there anything really unique about moto, or is it pretty standard to what you see for other sports that have helmet tests? Are they pretty much all linear tests per se for energy?
Yeah. Linear tests is primarily what being used in motorsport. In fact, that's all that's being used in motorsport. And for most helmets, it's all linear, primarily because the thing about testing, standards testing, is that it has to be repeatable. And it has to be relatively simple because a lot of people are going to do it. And so that's why to date, a majority of the helmet tests are linear. They are beginning to change, and partly because MIPS has been very active in terms of creating a rotational acceleration, a rotational impact. A lot of people don't understand how challenging it is to create a really good standard rotational impact.
Well, I think that's unique. The more I've learned about systems, and it's been really fun actually having so many different brands stepping in the market, kind of starting this competitive, I want to say a little bit of competitive war, which ultimately the consumer wins as brands start to push each other and accelerate the knowledge here. But I've also noticed a lot of it, what I see from data, what I hear, because there is no standardized rotational test, people can also be like, oh, we do really well here, but they're also kind of designing their own test. In the case for you guys to do one in moto, what would you look at when you were basically going to develop a test for moto? How many different versions have you guys done, and basically how'd you even get started there?
Yeah, I mean, you're absolutely right. And it makes it extraordinarily confusing because, as we all know, people who run sophisticated test labs, we can pass and fail any helmet you want just by the parameters we set for testing. But one of the things that we do that's important is, first of all, there's one test that's proposed in Europe, and that's the 1078. And so we look at that as being a starting point. The other things we look at, as I showed in the presentation, is we look at how the event is occurring. Because if we understand the parameters around the event, we can then use that as a means to establish a test protocol. And so once we've done that, we will then start with the drop system that's been described in 1078. We'll modify it slightly to make sure that the inbound velocities and the impact angles are correct. We use a hybrid 3, which is a three-dimensional, rotational, and linear, so we capture all the dynamic response. But that's really our approach. Our approach is to do an analysis of the events that create concussion. We understand the parameters, and then we replicate that with in this case, we use the drop system.
So I'd like to give, I got a couple other questions just related to testing and energy, but before we get too far down the rabbit hole, fluid inside itself. So, I mean, I was talking to one of the main engineers about this, and I saw the system a year and a half ago. First time I have a race helmet. I go to all the races, so I'm peeling apart guys' stuff, and I saw what it was in a helmet. And even just from seeing it, touching it the first time, I had a basic idea of what it was. The fact that it was either a gel or fluid inside a pocket, I kind of had an idea of how it could absorb energy, how it could shear, how it could move. But from the simple standpoint, I hadn't thought of in the moment, and the first thing that popped up on your presentation is think of the human head form as it is, the skull, the brain, and then the cerebral fluid that already floats around and protects the brain. That's kind of from the most basic explanation. It's kind of like you guys took your inspiration from what the human body already naturally does and expand upon that, yes?
We'd like to say we did, but we actually didn't. We ultimately realized it works because of that. But what we were initially, we had a lot of data on rotational acceleration on impacts. So what we did was we took those tests that we'd been doing, and these weren't standards tests, but reconstruction tests. And then what we started doing is looking at different materials to decrease the rotational acceleration. And we tried a whole variety of materials, and not surprisingly now that we understand the implications, but at the time, fluid became the most important. We had to use a very low viscosity fluid, and then it released the head, and from there we could then manage how we were going to absorb rotational acceleration or rotational energy. And of course, it makes sense when you start looking at the anatomy.
So something you touched on there was the recreation. So like I said, if you're going to come up with a test, you got to understand first off what actually happens when I hit the deck. So the lab you work for, that's something you guys extremely specialize in, correct? Is recreating events and incidents like that so you guys can understand how to develop the test, correct?
Yeah, that's our science, really, is exactly that. We're not a test house. We can do the tests, of course, and we set up to do them, but our real expertise is reconstruction of events.
So fluid inside the actual pockets, like I said, from a rotational standpoint, it makes sense because of the ability for the fluid to move. Does it also have basically energy absorption properties? And is it, I guess, in a sense, the type of fluid in it, is it speed sensitive in any matter? Like slower to harder you hit it, the way it absorb energy changes?
Not really. What we did with the fluid on shear was to try and get it as close to zero as possible. So there is no sort of adaptability. And the challenge around using a material that's rate sensitive is to get the right rate. Because the brain, of course, will be traumatized at different rates anyhow. So it's got to work through a wide range. So what we did is we decoupled the head by using as low shear as we could, and then we managed the absorption of the energy over a longer period of time by the pod characteristics itself.
Yeah. So basically, if I'm looking at if we had a graph that showed what, standard head form is going through an incident, what that peak energy looks like, fluid allows you to lower the peak, but you spread out the energy over a longer dwell period, or?
Yeah, that's really what we're doing. The risk you have to have, or the thing you got to be careful, and that is that there is a time base that if you prolong it too long, you can go back into the danger zone. So we run what's called a risk curve, and we try to drive it below that risk curve. And of course, one of our publications really describes a risk curve right throughout the range.
Yeah. So the other thing I had curious that you mentioned just about dealing with comparable to other technologies that maybe focus on rate sensitivity or speed sensitivity is how that rate or speed is decided. Looking at the human body itself, say eye impact versus somebody else here that's 4 inches taller than me and weighs 80 pounds more than me, even on the size of the head form, how much of that would affect deciding, like I said, you guys focus as much as possible on the lowering the shear quality. Is that what would make it difficult to implement a technology that's speed or rate sensitive? Is how much even the human body itself, can that affect all those forces by a noticeable margin?
I think it's not so much the variance in human anatomy, because even though you'll have larger and smaller heads, the mass doesn't have a huge effect on response. It has some, but the heads don't vary that much. So it's pretty consistent. The difference is that if you absorb an energy at a certain velocity, impact velocity, that's where you optimize it, and you get hit by a different velocity, and the material is not as effective at that rate, that becomes a problem. And that's why I think the rate-sensitive materials have to have that wide range of performance. You can't dial it into a very small velocity range, because you're not going to get hit like at that all the time.
Mm-hmm. The actual placement of a fluid inside. So I look at, like I said, a lot of people, the first thing they think of when they think of rotational energy is MIPS. They're really kind of the first major product, and the fact that it can be adapted to pretty much any existing shell because of the design of the product itself. Now, you guys, it is, from a simple standpoint, I'm holding a gel packet. How much does it matter on the way it's built?
Fluid packet.
Fluid. I keep saying gel. It's fluid.
No,
packet.
but it's very important
very
because gel
important,
has lower shear.
Lower. So having a fluid pod, how much do you guys have to be involved in the placement in the shell? Because I sort of understand, say, like how MIPS works and fits stuff, but then it's, there's also that end where somebody can just kind of take the product and fit it, etc. In your guys' case, how much of it is working with, say, Fox, when you're putting in that helmet? Do you just give it to them and they figure out how to fit? You give them information, or how many iterations are going back and forth with you guys to decide on the placement and size of them?
Yes, we like to optimize the performance, and it goes back more depending how complex the helmet is. Some helmets, they're so easy. And of course, the helmets, if you retrofit, they're not designed to use the technology. So for us, we've got to figure the helmet out, look for the best placements of them, and of course, a lot of helmets now have a lot of geometry on the inside, and that makes it a lot more complex for us to find spaces and interfaces. And so for us, sometimes 2-3 helmets, we got it, and it's very robust. Other cases, it can be very challenging. Not in the case of Fox, because we work together with Fox. So we sent helmets back and forth, and it was an iterative process in which we got it working really well. And then as they designed the helmet, they kept sending us revised prototypes that we would give feedback on. There's other helmets that with 20 different prototype testing, we still didn't feel we optimized it as well as we'd like. So it really is an interactive process.
What was your guys' first product on the market that used your technology? Was it in hockey, or?
Yes.
Okay, that's
CCM hockey helmets.
Okay, that was going to say the first time I've ever heard of this technology was hockey based. So
That's
right. How many years has that been now?
4 or 5 years, I believe, they've been running the technology.
Is this deal you guys were doing at Fox, is this exclusive to them, or for motorsports or power sports application per se?
In this category, in their categories, it is.
Well, last one is as a recap kind of for everybody, just from the most basic standpoint. If somebody walks up to you off the street and you have 2-3 minutes to describe to them what fluid inside is, somebody that really doesn't understand rotational energy, how would you describe it to them?
It's a technology that decreases the risk of concussion.
Man, that took 5 seconds. So I guess the last thing, though, is, like I said, because I kept saying, as I would say it, accidentally messing up, is gel. And the main reason behind the name, the fluid inside, is really when you say shear, for somebody that doesn't even understand that term, are we talking about the, I want to say the drag of the material itself versus what it's doing in the head? When you say shear, you're just talking about I'm trying to think of the word, like drag, resistance. That's what I'm trying to, yeah. So if somebody doesn't understand shear, you're basically talking about the resistance or drag of the material in the head. You're trying to bring that down to the bare minimum. To zero.
If we can get it to 0, all the better, because then that allows us to develop the characteristics of deceleration.
Awesome. Thank you very much for your time, sir.
You're welcome. Yeah, it's a really good question.
Hey, this is Michael Lindsay, and I have Dave Munn with me, who's a senior engineer here at Foxhead. And I know this amongst multiple projects here, but this has definitely been a big one for you for the past couple years, introducing the all-new V3 helmet. Let's start from the simple point. How long has this been in development? How long have you been messing around with it?
I think the team and I have been working on this for coming up on right around 2.5 years.
Is that, like, when you think of that as 2.5 years, is it like this exact design, like from beginning to end, or is that even include like rough project phasing, like before that, when you're kind of trying to decide what the next evolution of helmet would look like?
I mean, it's hard. Like, if we had to start from scratch to develop a helmet, it'd take much longer. But we're building off of our history with the helmet, and we partner with some world-class leaders that really kind of give us a leg up on the technology. So it's hard to put a real timeline to it.
What for you guys in development? What's basically the first phase of basically building this thing? Is it like what was the first technology you identified amongst the multiple things you're introducing into this thing?
Like I said, it's an iterative process. So we learned a lot from our, history of helmets. We've learned a lot from what's in the market, and we see where people are going with helmet technology, and we see where we want to go, and then we kind of evaluate what we think we can achieve, and then we come up with a plan.
Now, of course, the prior high-end V3, the prior top-end helmet for you guys, the old generation, it used MIPS. That was kind of as everybody started to wrap their heads, per se, around what rotational energy was, how it affected the brain. Everybody kind of went with the known quantity, the proven quantity with those guys. But since then, multiple helmet manufacturers have gone out to try to find, per se, their own spin or something that works better. And I think it's really cool just for the marketplace period that so many helmet companies are going different routes and trying different things, because it basically the person that wins at the end is the consumer. It turns into a little bit of an arms race, per se, as everybody's trying to one up each other. What was that actual span like, trying to identify what technology you guys wanted to use in the case of managing rotational energy?
It's really just evaluating what's available, evaluating what our ability to make our own technology, where we are there, and then, seeing where the research in the brain injury and concussion management, world, where are we in the world in that understanding. And we ended up partnering with, like I said before, a world-class leader that we feel is really kind of leading the charge in that aspect.
What led you guys to Fluid Inside?
So Fluid Inside, we've actually, Blaine's research, so Dr. Blaine Hoshizaki, his research, we've seen him on a lot of papers. When you're researching helmet technologies, you read a lot of white papers, and saw his name coming up quite a bit and kind of dug into what he was doing a little bit, and ended up finding out about Fluid.
What was, for you guys, what made it, per se, your clear-cut decision to go with them? What, from an engineering standpoint for you, what stood out about the technology that made it make the most sense to you?
There's a lot of things. It's hard to say one specific thing, but one of the benefits is that we can optimize the solution for each helmet. We can optimize it for the size. It's not a one-size-fits-all kind of solution. We can optimize it, like I said, for whatever helmet we're applying it to. That was a big factor that we really valued.
So the actual Fluid pods themselves, was there seven of them?
There are 7 pods.
So I remember seeing it the first time last year. I saw one of Roxon's helmets apart and seeing that you guys had retrofitted this technology into a prior generation V3 to start testing it. And I just reached in, kind of felt it, and quickly grasped, like, okay, kind of what it was. And of course, the initial thing that worried me is like, okay, there's a type of fluid or gel inside this pod. What does that mean for multiple durability standpoints? Like, can it be punctured? Can it wear out? What is the fluid made of, from a point that if something were to happen, is there a chemical issue, anything like that? I know you talked about quite a bit in the presentation, but there was a lot that went into the actual durability testing of just that pod, more than just a dude riding around in it.
Yeah, we spent a lot of time researching, like a new technology is risky, and you need to minimize that risk. And in order to minimize that risk, it's a lot of testing and putting it through basically what we call like torture tests. And so the pod is basically a sealed container it contains foam and mineral oil. The mineral oil is a food grade mineral oil that if you cut it, it will be safe to be on your skin, safe to be in your eyes. You can actually technically eat it. I wouldn't recommend it, but it's the same oil that they use in like food processing machinery. So it's a very safe inert oil.
I think you said really the only situation where you guys have one punctured, you literally either have to take a knife or an extremely sharp object and dig around in it, but from actual impact, you said it took 35,000 PSI to actually burst or even slightly break the pod itself?
Yeah, realistically, the only thing that you'd be able to damage these with while they're installed in the helmet is if you have a knife or a screwdriver or something that you really jam in there. But yeah, we put it into a parallel plate test and we compressed it. We wanted to understand what the burst strength was for these pods. And the first machine I put it in, I actually broke it. Went to a larger machine, and we ended up having a very high burst strength, and it was actually a pinhole. It wasn't a burst strength, a burst failure. So they're very durable.
To put it extremely bluntly, that kind of pressure, the general consumer would not have to worry about it, because if you were to impact in the helmet enough pressure to cause that, you wouldn't be very well off.
No, you would have a lot of problems you have to work out. But yeah, the pods will outlast the helmet.
Talking about some of the air technology, so one of the ones that stands out, it's becoming a little more, it's definitely been on the market for a while with, I know another helmet company kind of was one of the first to bring it out, but it's becoming more popularized per se, is, for lack of a better term, a lot of people know as cone head EPS.
Sure.
What's the exact term?
We use Verazorb.
Verazorb.
Yeah.
So it's basically two different sections of EPS that slide in this cone section together. Can you give us a little breakdown on what's the difference between having two flat slabs of different density EPSs versus actually having them cone into each other?
Sure. So the Verazorb is basically two different densities of EPS, and the two different densities manage two different energies. But what we're able to do is we can change the geometry of where the materials interface, and we basically add what looks like cones. That's why it's called cone head. And those cones basically add like a third energy management range. So as those two materials compress, those cones expand, and it changes the way that foam compresses.
So the actual design of the helmet, for anybody that likes to follow either Fox in depth or as a mountain bike and a moto person, they'll probably have noticed almost this helmet running around for the past month, because Fox introduced the Rampage Pro Carbon, your guys' professional downhill full face helmet. And typically in the past, a downhill helmet and the motocross helmet for Fox have had very different design features. Aesthetically, they look quite a bit different. Now going into this helmet, they're pretty close from a design standpoint to the same. Basically, where I guess there's two ends of the question. How much of that comes down to the design that you guys came up with, you knew could cross over between the two well? And then secondly, the way it's designed, I mean, to put it bluntly, the retail price of this is pretty good for a top-line helmet to allow you guys to sort of transfer some of the development costs between two helmets while executing the same end result of, pretty much checking off the list of what you guys needed to put this out there.
I mean, I really wish it saved money, but it doesn't save money. Really, the only thing they share is design language. The shells are all different. The internals of the helmet are all different. They're both 7-pod systems. They're both similar layouts, but really, the visor's different, the cage is different, the EPS is different. It doesn't share much.
So don't ride moto in a Rampage Pro Carbon, and don't ride downhill in a V3.
Do not do that.
I'm sad to say I found a guy on YouTube that talked about how great it was to ride downhill mountain bike helmets on his dual sport bike because of airflow, and I was so scared for him.
Yeah. Probably don't see many videos from that guy after that one, huh?
The other major aesthetic design that's noticeable is really, I think a lot of people are going to gravitate to two things. The side profile of this helmet is very aggressive. I love the side profile. The front profile is definitely something very different to get used to, coming from, like I said, I think mountain bike guys are a lot more used to seeing this much ventilation, a chin bar that almost looks like, basically, you notice it's a separate material from the main shell. Moto, we haven't seen a lot of this. What is the reason for that we're now seeing that in this helmet for motocross?
Yeah, so having that injection chin bar and eye port really allows us to open up the ventilation channels. If you look at a lot of helmets, the vent on the exterior of the helmet will look really big and impressive. But if you take the helmet, flip it over, take the liner out, you'll see that really there's only maybe one or even two pencil diameter holes. And by having this injection chin bar, we're able to support the backside of that vent. And why that's important is part of the DOT certification test. There's a test where they drop a spike onto the vents, and it needs to be able to support that spike. So that allows us to get that large opening and also the large exit that goes through to the head.
How hard is it to actually manage airflow along with the noise that penetrates to the rider? Because naturally, I think of the larger channel you have, yes, the more air that can come in, but also the more noise that simply can come in. Is that something that you guys actually work with on design? How, can you flow enough air that basically you'll end up with a helmet that is notably louder, and then are there ways to negate that through designs of the channel, the padding, etc.?
Yeah, I mean, when you move in air, it will make noise. It tends to make noise, so it's kind of a balance. You know, if you want to have a ventilated helmet, you got to move air. When you move air, air makes noise. So it's a balance.
And the last one is the shell itself. I know a lot of people are like, oh, I wear a polycarbonate shell, I wear a composite, I have a carbon fiber helmet. In this case, how many different materials do we have going on, counting the chin bar?
So if you include the chin bar, it's basically 5. So there's carbon fiber, Kevlar, fiberglass, and nylon in the shell. The chin bar is a polycarbonate ABS alloy, so 5 materials.
Weight of the helmet. So we were just discussing that depending upon the size. Medium, we're just coming in under 3 pounds, like 2.97, 2.96, depending on the variance. And then large is just above that. That 3 pound mark seems to be, 4 or 5 years ago, that was a really light helmet. Now that's starting to come into a pretty common for a high end, people dipping into the high 2s. Are you guys, was there a target for you guys when developing this helmet for the weight compared to the outgoing V3 or?
Yeah, we wanted to meet or exceed that weight. Weight is a hard topic as an engineer. You draw the analogy for cars, right? Cars in the 70s were potentially lighter, but they also didn't have high-strength steel, didn't have airbags, didn't have crumple zones. So as we add safety features, there's a weight cost to that. So it's a hard balance to minimize the weight gain, but maximize the benefit.
Last one. So the outgoing V3 kind of, in a sense, almost lived through multiple lifespans between having MIPS introduced. I think MIPS got introduced to it after its launch. I'm trying to think of that. Yes, because you had V4, V3. So MIPS got launched into it later, and then the MVRS, magnetic visor release system, got released afterwards, basically taking the current shell and retrofitting it. Personally, I'm a huge fan of the idea of popping off, but as we've seen a little bit of an issue, like for me personally, I've only ever had it come off when I've crashed, and I wear that helmet a lot. But as we've seen in a race situation with rocks and guys that are at the top level, getting roots to a lot, head down the way it leverages. We've had some visor removals during races. Like I said, that one was just kind of retrofit on a helmet. Now that you've had the ability to go and design the shell around having that visor system, what that allowed you guys to do? Did it allow you to, per se, fix some of those problems or improve the release of it and when it happens?
Absolutely. So we learned a lot from that Gen 1 MVRS. So the Gen 2, maybe we talked about it, but the geometry of the visor and where the visor mates to that cage, it's completely different. In addition to the magnet supporting it, the magnet also acts as a pin, but there's also a tertiary support that supports the center of the visor on that cage. So we've really gone through and made sure that this will perform as we expect it to.
As the engineer behind, this project, what are you most proud of in it? What do you think stands out the most as what you feel like was the biggest accomplishment for you all designing and developing it?
It's hard to put your finger on one, but it's just a really fun project, and the team did a great job putting it together, and the aesthetics are really killer on it. So I'm just happy with the whole helmet. The whole package is really great.